Hello, everybody. Welcome to our panel discussion. Unfortunately, our only one of the conference based off of our schedule issues yesterday. I'm now going to invite our participants on screen, so give us a quick second while I get everyone up here. Awesome, I see you, Steve. I just sent you the invite. Awesome. So we've got everyone up on screen here. So basically what the purpose of this panel is sort of to try to replicate some of the normal discussion, over a cup of coffee or lunch or something that you would get at a conference that you don't get at these virtual conferences. We've all been searching the past year to try to replicate that we've struggled to do. And so I'm very thankful for everyone for volunteering their time for this half hour. I think we have a great mix of sort of, people across the spectrum of, how long people have been in research, how long they've been running their labs, et cetera. So the purpose of this time for everyone who's here is basically for you to drive a discussion, from between our four panel discussions. Alexandra doesn't have her camera on, but that's okay, but she's here in the corner. And obviously Paula, Andre, and Steve. So please ask any questions that you have that you'd like to see drive this discussion with the Ask a Question tab. I guess I'll start things off. I think since we have such a sort of diverse range of interests and research interests here, that I think a nice way to start this is to ask a sort of big picture question of you all, which is, where do you see the field of computational neuroscience going over the next 5-10 years, especially for the trainees that we have in the audience who may be looking for a branch of computational neuroscience to specialize in, or a neuroscientific problem to apply their skills to? Do you guys see a currents in the field that are sort of driving things towards specific techniques, specific problems, or is that something that you guys still feel is very wide open? And I guess if you guys can we can have this be wide ranging, so speak up if you have something to say, unmute yourself. And we'll hopefully try to get an organic discussion as much as possible in this platform.
My impression is that it's a very good time to be in this field. Can you hear me?
Yep, perfect.
Yeah, I think a lot of computational neuroscientists find a home in research institutes and universities and companies now more and more. I think a lot of universities are waking up. Some have been really the trendsetters, but are waking up that, like, hey, we want someone like that in our department to collaborate with our people. And I've seen that more and more in Canada here in particular. There's just been a lot of hirings, and it's very encouraging. And these people can go into, from a university perspective, into biology departments, mathematics, physics, computer science, neuroscience, medicine. It's all over the place. I think that's a general trend. And yeah, I think it's a good time compared to 30 years ago. Of course, the AI gives that sweetness to the whole deal for a lot of people looking to. They'll say, like, yeah, we you do neuroscience, but can you do AI? We just come on in, right?
So that's an interesting point, Andre, which I always find flummoxes me, which is the buzzwords versus the content, right? Which is, are you doing AI? Are you doing machine learning? Whatever the buzzword of the day is. And maybe that's something more that, comes into play on the industrial side as opposed to, the hiring in, traditional academic institutions. But do you think that's something where an aspiring student should focus on something like AI, like, machine learning, deep networks, insert buzzword here? Or do you think that there's still space for the sort of, generalist, for lack of a better term, computational neuroscience?
I think they should just focus on good science, but that'll pay its way. But I think it's the new calculator, so you can't avoid knowing about it. So yeah, of course you have to learn how to do it, and learn some of it to be somewhat proficient and understand half the talks at these conferences. So I think it's but you have to decide whether you really want to be married to that discipline and sell yourself as that kind of person, right? That's a different question. But I mean, one thing, I'm going to shut up now, let the others talk. But I think I think what's going to happen is a lot of universities are going to hire and companies are going to set up core facilities in AI, machine learning, and they're going to want people who are not necessarily going to do the prof thing, tenure track thing, but they're going to just be very high level research associates to run these things for various groups and collaborate, and people who know how to interact with experimentalists and speak their language. So it's happening at our own place. It's happening a bit everywhere. So I think there's going to be a lot of nice jobs there.
Awesome. Anyone else have want to add on to what Andre just said? Steve, is your mic working now?
Yeah, I think so. Perfect. Is it? Okay.
Yeah.
I was just going to say, I think I agree with Andre. I think, there's different ways to make a career. And sometimes that involves, technical specialization. Sometimes it involves sort of generalizing so that you can actually take people who are, really highly specialized and link them together to create sort of synergy. And that's, they're different skill sets. So I think, in some respects, sort of follow where your interests are. I think it's hard to predict the future. And if you sort of follow your passion, get good at what you're sort of naturally, inclined to do, then you'll hopefully be happy doing it, and do it really well. So, I wouldn't try to micromanage, the future too much, because it's really hard to predict.
I have a comment to make on this. Can you guys hear me? Yeah. So one big problem that I notice a lot, you get return, I think. But anyway, I will continue. Is that when machine learning is employed, is usually because we're dealing with big data. And the problem with big data is that we don't understand their dynamic behavior. And it's very difficult to understand, for example, when you deal with biophysical models, what exactly their dynamics are. You have to simplify them to some simpler models that you can analyze. So even if you sell yourself as a machine learning person, if you want to be successful in what you do, you have to understand network dynamics. Otherwise, you can use optimization algorithms that just don't work for the dynamical regime where your network is currently sitting at. And that's a very common problem. And I see people facing it that are extremely competent, and they deal with these, with networks that are complex. But so it is a challenge for those doing machine learning. Many times, in an attempt to optimize those networks, they still need to somehow understand the dynamical behavior of the networks they're trying to optimize. And I think that's going to be a challenge in the future.
Well, this is going to sound slightly redundant, I think, but one thing that I find myself saying to more junior people who might be excited, maybe they want to join the lab, maybe they want to come to class, is that AI machine learning are tools. They are hammers. Just don't go looking for nails. Like, it's good you know how to use a hammer, but you got to be careful when it's time to use it. It will naturally lead you there. You will naturally find yourself in a place where you want to use those kind of tools for addressing some kind of question. That's when they work. In all other situations, it's not like they don't work, but they don't work quite as well as other things that you could consider doing. And so it's that, in my opinion, the buzzword lasts a season, unless it's really the season you're sending your job application out right now, then you really might want to pay the token to the buzzword. Otherwise, yeah, what you're hearing at all levels of expertise, I think holds true, which is if you know what you're doing and you are passionate about the questions you're asking and how you're shaping them, you have a much better chance at getting an invitation than just because you say the buzzword.
Awesome. I think I think everyone will be happy to hear that for sure. So we have a question from Marina, so I'll just read it off. So some types of hormone-releasing neurons in pituitary react only as an electrical stimulation of a certain shape. As a result, such neurons do not have much spontaneous excitation. Do members of the panel have seen similar behavior of other neurons? So I think this sounds like a more specific scientific question. I might not be doing it any favors, but I guess the core of the question here is have people seen neurons that are very sort of tuned to specific inputs? I think, Marina is asking in terms of hormones, but I think this is something that, we can ask more generally, which is how are people seeing these type of neurons that are responsive to very specific types of inputs, and how is that influencing your research?
I'll have a quick answer to that. Is I spent a lot of my career looking at sensory neurons, precisely because I know what the input is. And I've had fun doing it, but it's it's a different challenge when you're sitting in cortex somewhere where you don't quite know what the input is, right? And it's intellectually, it's a very challenging and fun problem as well. Both problems are good. So just, I think it goes by whatever, fires you up. But by and large, we don't quite know what cortical neurons still like, right? We're looking, there's lots of things they do like. They have mixed selectivity, in particular, and sensory. When you're at the periphery, they're more dedicated sentinels for specific things, and of course hormonal cells. Well, they're looking at the pituitary dynamics. They're looking at very specific concentrations to decide what to do about it, or temperature neurons or whatever.
Awesome. So we have another question, this one from Helsa, and I think this sort of builds nicely off of some of the stuff that we saw this morning. So he says, we usually look for stable states of neural network dynamics, but the brain seems to be more unstable than stable. Should we be studying transient phases rather than stable states? And how would that sort of recontextualize a lot of the problems, like the ones that we discussed in this morning's session on oscillations?
Well, in very short, yes. It took me 1.5 years to get out a paper that said inhibitory transients in the title. So it wasn't necessarily something that it's intuitive to propose, but I guess I might not put it in terms of an either or. I might try to put it more in terms of a landscape of potential dynamics that can be leveraged for computation, for organization, for understanding of the brain. It's just, to some degree, maybe stay open-minded. Don't jump to the first stable oscillator you can think of when you're looking at a problem. However, stable oscillators are very good to learn, first of all, what kind of mechanisms you have available. And also, like when you have an understanding of the stable picture, moving into the unstable or more stochastic picture or other forms of mathematical pictures that you can derive from that. It's a much, I would say, quote unquote, straightforward way to generate the new mathematical point of view, rather than trying to come up with a transient out of nowhere. And it could be harder, it could work, but it could be harder to have a sense of, are you near something that you can understand, that you can bifurcate, that you can converge to? But again, everybody should target their problems their way.
Yeah, I would say I agree. And go ahead, Steve. Did you want to say something?
No, I was just going to say Scott's muted. I
Okay.
can see him talking.
I keep falling prey to the go-to mistakes. I'm not showcasing my moderator skills too well. So Andre, sorry, I interrupted you. Did you have something to add on there?
Well, I agree with Paul. I think you have to if you have a dynamics bent, if you come from applied math or physics or engineering, then you're going to want to know what the skeletal structure is without noise, without transits and so on. That might be something very interesting or something very simple, but in my experience, if you want to really study transient states in the brain or transient states in anything, you have to start from there, and then that's the way to understand how noise is going to or modulation is going to flip you around. But if you come from a statistics background or probability theory background, then you might not care, and you say, we're just going to characterize this. We're going to do GLM models, or we're just going to do information theory. Who cares, right? And both are interesting approaches. You just have to see what is the explanatory power in the end. Again, I think it comes down to preference of what excites you. Right? But there might be some very good problems that have been addressed the wrong way so far. So and a lot of these things today, we just came up with a bunch of examples where if you don't consider the transientness of the whole thing, you're losing part of the picture. But this took an evolution to get here. We're building on a lot of past work.
Awesome. So we got Alexandra's video fix. I'm not sure why Crowdcast was being so finicky, but it's great to have her up on screen. So we got a couple questions coming in. Alex had a more general question, which said, given the recent growth of the field, what would you consider are clear examples of success stories in computational neuroscience over the past decade? And then what do you think will be the next quote unquote big thing?
Okay, there are a bunch of areas, and I think everyone would choose their favorite topic on this. It's impossible to be fair in answering this question. I have to say I am impressed by some of the advances in machine learning. Not that I am a machine learning or an AI person, but it seems to be the case that some deep network, some AI models, they can replicate some of the behaviors that we see using biophysical or more simplified models as well, and they can do it better. So I think we will be using a lot of the approach in the future where we're looking at a particular problem. We want to understand how the brain is generating a certain activity, and we're going to have an AI type model learning that task or generating that activity. And then we will be looking at the deep neural network, how it implements that activity, how it learns that activity. And then we're going to be trying to draw parallels with the brain and say, is the brain learning in a similar way? So like it or not, I think this is going to be an advancement in the future. It's going to be one window to understanding the brain, like drawing parallels from how deep neural networks work to how biophysical networks work. And yeah, it has made some advancements that are quite impressive.
I was just going to add, I guess it's interesting also to consider those areas that have not really changed much, and that might be sort of ripe for this. And I guess what I'm thinking about is things like homeostatic plasticity. Recently, I hosted Gina Turrigiano for a talk, and sort of looking back over 25 years of her work, and just thinking sort of, yes, there's some work on synaptic scaling, but other aspects of things like intrinsic excitability, that really haven't changed. And I think now where it's possible to get more and more data, what's going to be possible when sort of big data approaches get applied more broadly than where they're being applied right now. And I think there's great opportunity there. So in some sense, looking outside of what the success stories are and seeing where the opportunities are is also really quite interesting.
I think there's going to be some very interesting work coming out of social neuroscience as well. So I think that's going to be a big field. So animals, just you can just record from prefrontal cortex of animals, and you'll see the cells respond in one way if there's no one else around. But if there's a conspecific around, they'll respond in a different way. So the whole social scene is not just the mirror neurons, but I mean, we're just mirroring at all kinds of levels. I would kind of run into that field if I had a lot of time left. So, but you have to find the right experimentalist to work with. It's not an easy thing. Recording from animals in a collectivity is not easy.
Awesome. So I'm going to keep things moving. So there's a question I think will be of interest to a lot of people, a lot of the trainees, and obviously we're all academics right now, so this might be, something that we only know about tangentially. But Jack asked, what are the sort of career prospect or potential paths for people who want to do computational neuroscience work in industry? Or perhaps not necessarily do neuroscience, but use the skills from their computational neuroscience training as applied to industrial research or industrial settings. Does anyone have any knowledge of that?
I can say a few things. So we have to keep in mind that everything, computational sciences are now at their peak, and every industry uses models. Any industry you can think of. We can take the example of the COVID vaccines and how much they were supported by some early computational modeling. So if any pharmaceutical company that looks at the design of drugs and how they're going to target the brain and affect the brain, for example, would definitely benefit and utilize computational modeling. So I think we wouldn't feel as hesitant as in a couple decades earlier, where we could probably only could place ourselves in academia. I'm certain there are going to be opportunities outside of it.
I mean, the big boxes, the Google Mind, Facebook, just to give an idea of the big box, they're hiring. They've hired some of my students, so they're being hired. There's some avenues, of course, in all the AI social networking world.
Elon Musk's Neuralink also is hiring now.
Yeah. And everything down from there. There's a lot of startups in wearable computing, bionics. I mean, if you go to IEEE meetings, I think you'll see a lot of interesting booths.
I think the skills are quite flexible. They can be applied in different ways, and you sort of be I think people might not appreciate how useful those skills are, like the breadth of application. But industry, I think, can see sort of knows they need these skills. They don't really know necessarily what they need, but they're looking for people that can solve problems, and there's a lot of diverse, interesting problems out there that as people have said, you need sophisticated modeling to deal with.
Awesome. So I think we'll do one more question and I'll let you guys go. And again, I thank you for volunteering your extra half hour here. So Guillaume had a question. So despite the advances in computational neuroscience from invertebrate or simpler systems, there still seems to be a very strong focus on mice, rats, and humans. Do you think that we should look more at these simpler systems and have an evolutionary perspective about these higher order functions from simpler systems? Or is it time to really keep focusing on the complex systems like mammalian systems, like the human brain, which seems to be where the field is going? I'll just say real quickly, I would say that I think, part of what makes computational neuroscience useful is that it can answer questions from these more complex systems, especially where it's more difficult to get experimental data. In my work, one of the things that computational tools are so useful for is for getting the most out of human data when that data is limited relative to what we might get from a simpler setting. So I don't necessarily think it's one way or the other, but I do think that, you know, computational tools are uniquely powerful when it comes to these higher order complex organisms where we perhaps can't investigate things in as much detail like we could in these invertebrate systems.
Yeah, I would agree with Scott. I don't think that neuroscience academia is organized in this ordered fashion where we solve all the evolutionary problems and then we move into mice and rodents in general, and then we go on to primates. In reality, we're just working across those fields at the same time, and there are still people who are very much interested in solving evolutionary problems that have not been solved yet, and people who are interested in humans. And there's no other way, because we need to make progress in helping humans and in understanding the human brain. But at the same time, we cannot ignore understand what the foundation of brain function is by studying those more simple systems. So everything happens at the same time, really.
Yeah, I can maybe comment on this as someone who worked in snails in my early days. That experimentally, it actually became easier to do work in mouse and rats, and you had tools that you did not have in some of these other systems. So models sort of come and go. Their benefits from an experimental point of view can wax and wane, and I think you sort of have to adapt to that. And so, that said, there's still great utility in something like the somatogastric ganglion and work done by Eve Marder and her colleagues on things like homeostatic plasticity and degeneracy. So there's still room for that. But I think, from a comparative approach, that's great in terms of trying to put that together. But I think you'll find that people shift towards where there are tools and where there are opportunities, and old model systems get left behind. Other ones might, be renewed, as for instance, you can start doing electrophysiology in Drosophila or things like this. They have a new sort of edge, but as I say, it really it's really an opportunistic thing, I think, in many ways.
I was going to say one extra layer to these very, very valid points. At least through my postdoctorating, some of the best projects I was in actually had both. They had people looking at humans, people looking at animals, and people trying to do models while learning all these moving parts. So I'm not sure there is an either or, even within a given project. You can make an interdisciplinary project, have the right team, and have, of course, an extra layer of wanting to understand what other people are doing and where they come from in that, but it can be very gratifying to actually try to connect both.
There we go. Got to unmute myself again. I think that's a perfect place to end this. I think the interdisciplinarity of everything that we do and everything that sort of computational neuroscience aims for is, one of the coolest things about our field, in my humble opinion, and hopefully something that people have gotten from all the talks in our meeting here. So I'm going to shut this down now, make sure everyone has time to take a break before our concluding session in the afternoon. Thank you so much to Paula and Andre and Steve and Alexandra for taking the time. Hopefully everyone here got a little something out of this, that discussion that we miss so much at the in-person conferences, and hopefully knock on wood, someday soon we'll be back to that. So again, I'm going to shut down now.
Thank you.
Thank you guys so much, and we'll see many of you back at 2 for the next round of talks.
Okay.
Thank you.
Bye-bye.